Hey guys, welcome to the tutorial using the R language in order to do all the different types of algorithms that we want to do for our project. So I have just an R script right here that I'm personally going to be using in order to do this, but I will be giving you an R markdown that's going to kind of look something, excuse me, kind of look something like this. That will walk you through kind of how to set it up, how we're going to manipulate the data, and then the logistic regression, linear discrimination, quadratic discrimination, support vector machine learning, and partial least squares, and where you kind of should be kind of questioning yourself in order to build up your presentation. So that being said, let's talk about how this data is going to go. So you need to be able to load up all of these packages. For R, it should be something very simple of install package that. It's going to be in the R Markdown. So if you don't have these installed, never fear, it will happen. So I'll run those quickly. They're already loaded into my environment. And the next thing we're going to do is we're going to attach this packet or this data set called con. And so essentially for if you want more information on how I'm doing all of this and like background information on maybe the statistics of everything on it, I pulled a lot of this from this book. These are some of the practice, like how they set up some of the practice questions at the end of the chapters, and I will link those chapters as well too. This whole book is completely available via PDF. You do not need a physical copy like me, unless you're old school and you like copies of books like that. So this is completely pulling from a data set that is one that you can play around with, often used for testing different things. Oh, would you look at that? Things are masked. So what that means is that I already had things loaded. That's fine. What we're going to do is we're going to take these information and we're going to start setting up the data sets. Okay, so what does this mean when we're setting up the data sets? So the con data set is actually a gene expression data set. It is, if I'm not mistaken, one for different types of brain cancers. And you'll see in the code later on that I will determine them as types 1, 2, 3, and 4. So we can see in the dimensions that we have a total of 83 samples and 2,300 genes roughly that are associated with this data frame. Yours will be slightly larger. That is totally fine. Just means you might want to divide and conquer who is doing which algorithm so you're not clogging up your whole computer all the time. Anyways, the other thing that you can see is the Y. So the X for our supervised machine learning algorithms that we'll be using, or unsupervised, will be the gene expression data set. And the Y is just the variable that is associated with it. So for your data, that's going to be if it's MCAV, OAN, pstrake, or PAST. So this is also this is the page that I pulled it from, so page 588. This is the resampling approach from chapter 13. Essentially what I'm going to do now is I'm going to make 3 different data frames, and we'll look at what they look like after we're done. So we're going to do X with features. So essentially we're going to bind this information together. These data frames don't actually come with like the true names of the genes or the samples. So I'm going to populate that. You don't have to do this for your data, but for the purpose of doing the tutorial, I am going to do it. So essentially what's going to happen now is, so if I look at my information, I should be able to look. Well, normally I can see it over here. Yep, here we go. Okay, so I'm going to click it. I'm in RStudio, by the way. I find it easier to work with, especially if I have a lot of different tabs open that I need to be working on or different things. Okay, so the X with feature, the biggest thing that's going to happen with this data set is that we're going to see the way that we were binding it together. Go back to that. So I bound the Y variable to the X data frame that we already had. So essentially what that means is that we knew that the samples were the row names, and we knew that the columns were going to be the genes, or at least I knew that ahead of time when I was building this. And essentially what this is that now that Y variable is going to match to each one of these samples. So sample 1 is going to be a type 2 and vice versa. So you can see that. And if we go all the way to the end, that's where we'll see it bound. So that part just will take a second to populate. If we go all the way to the end, there it is. So you can see type 2, 2, 4, 4, 3, 1, 3, whatever. Okay, so that's how this data frame is set up. Depending upon which one we're looking at, I think all of them are the same for this one, but we'll walk through it as we go through. You will want to make sure that your data, when you get it, is going to be samples in the row names and the column names being genes. And there's a reason for that. Okay. So the one thing I will suggest you guys doing is that most of the algorithms that we're working with are going to be binary. And so what that means is that they're going to want it to be in a 0, 1 instead of having it be a variable that has like a name associated with it. It wants that number. So this is from the dplyr package, and I am mutating essentially anything in the type column. If it's 3, it's going to be 1. If it's not 3, then it's going to be 0. So you can replace this with your information, such as mcav will be 1, everything else will be 0. So I'm just going to do that real quick. And so now if I were to look at my data frame, give it a second. Actually, we can just do X. Don't want to do that there because I want to keep it down here, X with feature type. Now you can see now they're all going to be 0, 1s. Okay, so the other thing that I am doing here when I'm setting up my data frames is I'm going to create a train data set and a test data set. And this is going to be that 80-20% ratio that I talked about. And so for your data, you're going to want to do the same thing as well too. And that's just going to create those data frames. So I'm just going to quickly just run those through. And ta-da, now we have those data frames. And they're going to look exactly the same, 20 observations. Those are the 20 samples, 63 observations. Those are going to be 63 samples. They all have the same gene numbers because it's all the same all across the columns. It's just the rows that we've shortened. Okay. So the first option is logistic regression. Okay, so this example that we're going through, there's a couple things that I want to make sure that you're aware of. This is coming from, I believe, the ISLR2 package. Shouldn't be anything else. And it's also a base function in R. So you're going to build a model. So as this is running, it's fairly quick. Essentially, there's a couple different things that you need to make sure that you are putting in there. You need to include what variable everything's going to be tested against. So that's the first thing that goes in. That's your type. In this scenario, we're using type. And then the other things is what you're going to be testing it against. And essentially, it's anything that's a column. So this logistic regression is one feature to one variable. So I just did examples of column 2,250, just a couple different ones. for the data, this, just for the purpose of this first round, we're going to do X with feature. So this is training the algorithms with everything associated with it. And the other thing that has to happen with this fall, so this is just a general linearized model. In order for it to be truly logistic regression, we're going to need the family to be binomial. So now we can take a look at the summary of the model itself, and it'll tell us some of this information that we already know. So it'll tell us the call. It'll tell us the deviance residuals, so the min, median, first quarter, third quarter, max, all that kind of fun stuff. The interesting part here that's interesting for you to take a look at is going to be those coefficients. So this is the intercept over everything, but what you're looking for is these p-values here. So you're looking, this is how you look to see if something's significant. And as you can see, these genes are not very significant. So what this means is that this one doesn't have a significant anything really, honestly. And the AIC value. We can take a look at the coefficients as well. So that's kind of where the intercepts fall. It's not really that great. Not that I was expecting it to be. So let's take a look and see if we can predict the response. Just kind of walking through. So this is what it's taking, is that can it predict the type it is, or how well could it predict the type using that? And so all of them are saying it's kind of low, so it's not going to be a 1. So if we were looking at that, it's definitely not a type 3, which is good. It's not saying it's a 1, which would indicate that yes, it is, or it's most likely that. And we can kind of look at it from a probability perspective. So what we're doing here is I'm mutating the probability into, if it's above a 0.3, that's because this data set isn't very good. You're going to be wanting to look for a 0.5 or higher, preferably higher. You want the probability to be very strong and in your favor. Like how we talked about with those ROC curves. If it's 0.5, then it means it's like a coin flip. We want it to be much higher. But essentially, so we got that. The other thing that we're going to do is we're going to bind it into a little table, and so that we can take a look. And so see here, this is that table that I was talking about. So this is the prediction, and this is the true classification. So the prediction 59 to 59, great, but it predicted 6 of them to a 2. Now keep in mind, this is above 0.3. So this is not the best. And you can still see it's misclassifying a lot. It's not being able to find, it can definitely tell when it's not a type 3 stage cancer, but it's not doing a very good job of finding what is a type 3 cancer. So then we can take a look and summarize it. So this is the mean, so how good it is at predicting. And essentially, it's 75% capable at a 0.3 level probability of determining what we are working with here. This was just a walkthrough example of if you were to put everything all into your testing and training, what you should be doing is actually this portion, which is the better version of it. So instead of doing everything, you're going to put that train data set in. We're going to do that. We're going to fix this. Okay, so then the next thing that's happening here is that we're actually predicting using the test features. So this is going to tell us how good it is at, like, if you train it with one portion of the data set, how good is that model actually on data that we know what it should look like. So we're starting to see a little bit better. So the probability is a lot lower. Here, if you remember, if we go back up, you can see how high it was. So potentially using the training versus the testing is the way to go. So let's do this next part. I'm using again 0.3 because overall this data was not very good. I don't think we actually got enough that got over 0.3. But let's take a look at the score. Okay, so this is looking at the test data. So we can see again that it's really good at determining which samples are not type 3, but it's still completely misclassifying all the ones that are actually type 3. So it's going to say a high score, so a high predicted value. But like, it's really just because it's good at telling what it's not, which isn't really helpful. So if I was looking at this output, I'd say definitely these genes here, not great at being able to calculate what is a type 3. So these, from a biological perspective, me looking at this, okay, so this gene, and this gene have no predictive capability, essentially, for me to determine what is a type 3 cancer. Just toss those. For your study, you're going to have to do more than just 3 genes. There's going to be about, I think it's about 17,000 genes. Don't quote me on that. You'll see it in your CSV files. But something around there. So you will be able to use that you'll have to look at all of those. And there'll be ways to see that. We'll go forward with that later. Okay, so the next one is the linear discriminant analysis, and it has a very similar kind of like nomenclature associated with it. Instead of the GLM, we're going to use an LDA. Similar thing. What are you testing for? What's your feature you're testing for? What are the samples that you're training it with? What's the data itself that we're training with? So let's run it and predict. Okay, so we're going to have in this one, we're going to have class, posterior, and X. And so we're going to pull that class information out. And we're going to pull the information for the type, and then we're going to make that table there. So this one, it's classifying everything. Well, this is correct. This is completely incorrect, and it's classifying basically everything as a 0. That's not great. If we do the mean, it's saying it's 70%. But again, if you look at this table, it's really not what we're looking for. We're wanting something that's going to be a 14 here and a 6 here, because we want those type 3s to be able to be classified. Again, it's really good at classifying what's not. And we already know from the logistic regression that these genes are not very good at it. So I mean, what was I expecting? But there's a couple other things that we can do with this. We can look to see how many genes are greater than or equal to or less than or equal to. So you can see here those results. And then we can look at the posterior. So this is most likely for it being one or the other. These values aren't great. And then you can see the sum again. So essentially for me, if I was looking at this, if this was my algorithm, I could determine which genes are going to be capable for me to predict using these calls here. And I would use this table and this mean to determine A, how predictive my model is, like how good is it overall, and what it's actually classifying well. Is it classifying the thing that I want? We'll see. Okay. So that's LDA. The next one that we're going to be doing is quadratic discriminant analysis. Again, all of these, if you want more background on this information and why some might be better picked than others, because quadratic, linear, and logistic regression are all kind of like categorized as a kind of logistic regression. but certain data will fit better based off the distribution. And all that information, again, if you're interested or trying to apply your own information, you can use this book. Highly suggested if this is something that you're going forward with, or you know you want to be using this in your own research or something like that. Highly suggest that. Even if you're not going to be someone doing biology in the long run, this also includes stock information, all that kind of stuff. I just keep talking about this because I really wish I had this at the beginning of my dissertation instead of diving through papers, constantly trying to find someone who had code up and available. But anyways, back to quadratic discriminant analysis. It has a very similar formula as the last one. We're going to go and start with the training first and then predict with our test features. Okay, so we can look here, we can see the calls, the prior probabilities of the group, and then the group means. So we have, again, those class posteriors. There's, again, more background information on that. I'm trying to help you get to what you need in order to get to your class, but there's definitely, I don't want to undermine the importance of this data. I'm just saying what you need in order to answer your question of what's the best classifier. This isn't the primary information you need in order to do that. But you will need it. You will need that other kind of information if you're going to be applying these algorithms. Okay, so again, we're going to take that class information with the type, make a confusion matrix. This one's a little different. So we can do a confusion matrix, which will provide more statistics out of that. So test feature class, so you can see, again, not great at classifying it. So this is the test features, this is the class, you can see still not doing great. We can see the accuracy, the confidence intervals. I mean, those all look pretty snazzy. And the p-value, but the p-value is trash, which is what we expect because these genes we already know are not doing that. We have a McNemer's p-value test, and we have sensitivity and specificity. So this is kind of what are those X and Y values for that ROC curve. You will not be required to do this in this class, but this is what we are looking at for that. So we can see that it's sensitive, but it's not specific. And we can tell that based off the confusion matrix. It is sensitive to what is not type 3, but it's not specific enough to be able to indicate what is a type 3. Okay. And then we can get that mean, which we've kind of already gotten, which is a 7 detection rate. Okay, so again, so if I was the person in charge of doing quadratic discriminant analysis, I can look at this, and there's no reason why you can't do the confusion matrix on other tables. Wink, wink, if you want to try this in other places. I would suggest maybe trying that elsewhere. But if I was looking at this and this was my data, I would say for sure, just like how I said for logistic regression, these genes are not specific enough to be able to provide the classification that we need. So these genes biologically are not relevant to what makes a type 3 tumor a type 3 tumor. So we can toss them in the trash. Okay, so now SVM. So all the previous ones that we have done before are a 1-to-1. So what that means is that it's one gene to one feature. Sometimes biologically, it's not going to be one gene. Like they say smoking gun, they say all this kind of stuff, like the end all be all gene, one gene to rule them all. That sometimes doesn't happen in biology. Not everything can be a BRCA gene. Oftentimes it's a network of genes. So what that means is that there's biologically a group of genes all together that might be relevant to a classification of interest. And you will need some programs that can help you find a network. So SVM is one of them that can do that, and it can tell you which ones have the best capabilities. So SVM is going to be slightly different in how we are going to operate this. We're going to run the E1071 package in order to do SVM. We can see here the train and test, and we can look at the table for that. So we can see how many are in which ones. We're going to create a data file here. So this is pulling basically directly from the book. So we're going to create this stat. Also, if you kind of how we did before, if you're ever curious about what these are, they're all going to be here populated for you in our studio. Okay, so now the actual SVM. What you're going to do is how this is built, and again, this might help you with the loop situation that are not having to do a loop, but instead of listing genes, this will be helpful. So essentially the SVM is built that you have that. Y is now your type. This is calling all of the genes, this part of the code here. Your data is your data, and then SVM requires a kernel. So the one that we're choosing to do here is a linear kernel. There's a couple different options for kernels. It depends upon what your data kind of is distributed like. We're just going to stick with linear for now. And that's kind of all I'm expecting you to do for the project. But just know that there are other options there, and sometimes those might fit your data better than others. And then the cost. So now we have summary. You can apply more or less cost to it as well. And we'll kind of get into maybe why you want more or less. Okay. So the summary of it is that we can see our formula, we can see C classification, radial cost 10, number of support vectors 62, the distribution of them, 4 classes, and the levels are 1, 2, 3, and 4. So now we can take a look and see how this algorithm fit certain samples and how it actually was distributed. Okay. The other cool thing about this is that you don't have to manipulate the data with SVM for it to be binary, which is super exciting because now you can look at all of them at the same time. And you can look to see that this one, with utilizing a bunch of the genes, or the majority of the genes, you can see that it's classifying really nicely. You see that 8 to 8, or 1 to 1, 2 to 2, 3 to 3, 4 to 4. There's absolutely no misclassifications here. This is a really solid algorithm. And so how we can determine that is that we can take a look and see how well it's predicting now. So let's take a look. Okay. So we can see here that there is some misclassifications with 1 becoming a 2 or becoming a 4. But if we're specifically looking for 3, we're going to be looking at that. The big thing here is that it seems to want to classify everything as a type 4, which is not really helpful because we're seeing here that that's not going to be the best for us. And you can use that mean information over there to determine kind of over there how to determine the actual value associated with it. But as great as it looked here, whatever this training data set wasn't actually helpful in identifying it. So sad day, the SVM was not great at doing it. Sad. Okay. The other thing, okay, so side note, because we're going to talk about biology for a second, because this is a biology class, and we need to understand why this might happen. If you're throwing all the genes at this, we already know from the previous ones that there are definitely genes in there that are not helpful to identifying certain types. So if you're throwing all this information there, it might not actually be helpful to determine what is there or what is helpful. So maybe, if we're thinking out loud, I just didn't pick the correct genes, and there definitely are genes that are going to be helpful. Or having all the genes that are expressed is creating too much noise and we're unable to actually classify correctly. Those are some of the options. there are ways to kind of determine which genes are best at predicting with your SVM models, which we can talk about kind of how these look. You might want to change the cost, that kind of thing. We can look at the X scale associated with it, kind of see which ones are the best, that kind of stuff. And more of that is in your book. That kind of stuff. But all of that information will be somewhere in here. Okay, so now for the final one, how we're going to run it. So this is a partial least squares. This again is another one that will use all of the genes together at once. And we're going to do a new thing in here, which is the cross validation. So essentially that is a way that we can, it's better explained in the books, so I'll let you look into that. But a cross validation is needed in order to determine which genes are the best for fitting the model. We're going to let that run. And so I'm doing it with the X with feature first to begin with, just to see how everything is going. And so essentially, there's a couple things happening here that are outputted. We have the data dimensions, the how it's fit, the components being considered. So it's considering 73. And essentially, cross-validation is using 10 random segments in order to check for the validation for it. And so for each of these, it's components. So essentially, a component is kind of how we talked about with partial least squares. It's going to be able to build a visual in the long run that will be put onto an X and Y coordinate. So this algorithm is looking at what genes are causing the most variance to cause the separation between your features of choice. And so you're looking to see what's going to have like the greatest impact to it. And that comes from the percentage of variance explained. You want something that can explain a good amount of variance, and it will additionally add components as it goes along. So that's why you can see after a while it becomes 100% because you're using all of these components in order to explain the variance. So we really only need to like 5 or 6 components in order to completely explain the variance or aka the variation between our samples. And we can look at that with the validation plot. So this, we're going to start with looking at it with the train. This is how you should be running everything. Let's let it run for a second. And we'll talk about how we use this validation plot in order to pick the number of comps that we want, or how you should. So validation type is MSEP. Again, the book will explain that a lot better. But essentially we're looking to see kind of, you want the least amount of errors possible. Normally the graphs look like that. They decrease in the number of components. This data obviously isn't working very well with it. We're just going to keep chugging along to keep showing it. I'm choosing 9. But I chose 9 because I looked at this training variation and essentially I saw that like at 9, it seems to kind of fit. Actually, I think I'm gonna go 5 this time. Spice it up here. Okay. So this is our mean capability. So we're looking at the predicted values minus the test values, square it. So that's that. It's not really a great number. It is what it is. And this is just back to where we were. Okay, so overall, kind of what we have seen here is that whatever this data set is, we're not seeing that, at least the genes I selected were not good at predicting type 3. And that the noise from everything muddles too much type 3 in general. Or being able to classify in general a type. So for your project, you're going to have to walk through each one of these and be able to say how good it was as a classifier using these variables that we have here. You might not get one that's the best in the world. Like it might, these are just 5 very popular versions of it. Clearly with this data set, with these types, none of these were the option, and that's okay. Sometimes, like how I said, there's different validation types, there's different kernels that we could be selecting. There's a lot of different options based off of how the data is distributed. And so whatever was selected here was not the best for this particular data set. That's okay. Your data set might show something similar too, and that might lean into what the biology could be saying. So like how I was going through all of this, let's think about what that means from a biological perspective. Are we looking for one gene to one variable? Are we looking for a network of genes to one variable? Are we looking for just the overall best classifier? Are we looking for something that is a little bit more nuanced? These are things that you should be thinking about as you get these results, and that's going to help you finish your report. And the report will look something like this. You'll go through, you'll give your results, you'll say exactly how you got them, and if you would support this as an option or not. Hopefully it will not be too much of your time, because as you can see, it took me roughly 30-ish minutes to go through all of this, and I was rambling about biology during that. Might take you a little bit longer to go through the biology and what that means, but it is good to think about things. Critical thinking is very important. And you're not trying to solve the symbiosis question here. The important part for you is to learn just how to be able to read these outputs. That being said, if you have any questions going forward about how you might want to apply this or how this works overall with your project, please feel free to reach out to me. I will be able to help you, especially if it's in R, because R is my primary language. Good luck, you guys.